try?
Yes.
Screen share, custom. Screen share.
It's just Discord changing its settings.
Selection. Do you share this window? Nope.
Is there no option for a Chrome tab when you share your screen? That's what I see.
I am not seeing it. Let me check. Maybe I need to change some permissions. Let me.
If you make a selection, it should allow you to share the entire screen.
See.
Yeah, if you're on a MacBook, you might need to restart Discord after permissions have been given, and then you can click share screen and you can select the monitor all the way up to the top right, or any window you have access
probably need to restart. Yeah, restart Discord. Sorry.
Yeah, no worries at all. Yeah.
Yes. Give me 3 minutes. Sorry. Let me first make sure the permissions are on.
Yeah, let's just wait another 2 minutes, folks, and then I think Dmitry will join back. I can see Dmitry in the audience.
Right. Okay, I think it should work now.
Okay, awesome.
Okay. Let me see. Screen share.
Yeah.
Let's see. Can you now see my screen?
Yeah, I can see your Discord, but you might have to switch.
You might just put it again. You can't see the PDF.
But if it's on the same like desktop, you can switch, right?
Yeah, so I'm switching to the PDF, but it's not showing on the screen share.
Oh,
let me see. I think I gave it permissions.
Do you have to switch screens?
Let me see.
Otherwise, you can drop the PDF and I can share it to whatever works.
That might be. This is strange. Yeah, sorry.
No worries at all. Yeah, Don't worry, it's not you, it's Discord.
Yes, definitely that Discord is allowed to share screen. Let's try this. Screen share. Oh, pick selection. Yeah, so you really can't see other windows, right?
Yeah, but if you have it, you can swipe it. It's a Mac, right?
Yeah.
Yeah, you can just swipe it, you can move it away. Yeah, I can see it now.
I think great, perfect. Okay, can you see? Okay, perfect. I think this worked.
Great. I'll also mention that we can hear ourselves in the Discord. So if possible, it would be great if you can share just the PDF.
Yeah, I think
Then
now.
I don't think we get the audio from Discord.
Great. So I'll mute my volume, or maybe actually I'll get earphones. Thanks for saying this.
Yeah, there's no echo on the from your camera or from your physical feed, just from your screen share since it includes Discord.
Yeah, that's not a problem. But you can still see yourselves now?
Yep.
You can still see yourselves now. Okay, so let me.
Or we can see the PDF. We can hear ourselves. So we see what you see.
Let's see.
But we get the audio from the Discord client on your desktop.
Let me see. Oh wait, I can share entire screen. Perfect. I think this should work now. Wait, can you see my screen now?
Yep.
Okay. And you can hear yourself. So maybe I am going to.
I think it might be fixed actually since you went full screen. It's basically which application is in focus. So if this is the setup, then that works perfectly.
Thanks, great. Okay. I'm just in case gonna put on earphones. And let me know if there are any issues with the volume or yeah. Okay. Can you find? Can everybody?
Yes.
Yes, sir.
Great. Okay. All right. So I guess I'm supposed to end this talk at 11, but hopefully so people can stay a little longer if they feel like listening to this. But yeah, I'll try to give a pretty quick 25-minute talk and take questions if anybody's still around. Paul spoke about a kind of idealized interpretation of neural networks that in fact you do see in realistic systems, but it's kind of going from the direction of understanding some process in the data, so the Bayesian learning, deciding how one would maybe in theory learn it or implement it, and seeing this in the network. But there's of course another part of mechanistic interpretability, which is looking at a network as a messy system built in a particular way with neurons in particular architecture, and then seeing how the particular architecture implements certain problems, learning problems. And the two approaches have in common, in particular with Paul's Bayesian learning picture, which is that neural networks are statistical objects. There's many ways to understand this, but in this talk, I'm going to mostly talk about the randomness in weights. So remember that a neural network is trained by initializing at a random weight, and then finding a local minimum that will in general kind of at least be either be close to this random weight or be somehow attainable from it. And of course, there are other sorts of randomness in training process, but the weight randomness can in particular be understood in a certain physical way as some large random prior that then gets conditioned on data. If you do this, in fact, there are some contexts where physics gives you a prediction for what happens, some simple neural nets in certain limits, which are empirically confirmed. In particular, some aspects of these empirical observations coming from physics seem to persist for real networks, like LLMs. And so one observation that is very universal is that weights of trained networks are surprisingly close to the initialization. And so what does this mean? This means that while there certainly exists some kind of nice Platonic idealized processes inside neural networks, like the one that Paul explained, the entire weight assignment is very much not Platonic. It's very, very random because the initialization is random, and we just observed that neural networks actually only explored a small area away from the initialization. And so all that initialization from the randomness is essentially still present in the weight of a fully trained network. So I mentioned that there's a physics perspective on networks in certain limits. This is a classical perspective called the neural tangent kernel, but in particular it predicts Gaussian fluctuations that somehow understanding a neural network is like understanding something called the Gaussian process. So it's a particular statistical model and conditioning it on some observed data. In this process, we observe a certain kind of Gaussian sort of fluctuation, which is closely related to this initialization randomness, and it's again observable in both real networks and in idealized physical systems that these seemingly random effects are actually used. So this kind of randomness that if you were kind of naively looking at it and trying to find circuits you would view as noise, is actually used for computations, for certain clustering procedures, and even in some cases for generalizing. But at least in toy models, and to some extent in more general models, we can sometimes understand these phenomena and separate them from genuinely useless noise that we also know exists in models. But the problem is that current interpretability methods, so for example, sparse autoencoders, which in some sense, I think sparse autoencoder derived methods are the best way we currently have of mathematically decomposing models. But basically most methods that we have that we can actually apply in real life completely fail to find these fluctuation effects. So these are some effects where the neural network looks at the randomness at initialization and kind of uses this randomness, uses some kind of freedom of conditioning on this randomness to and kind of adjusting weights to kind of to take advantage of some random effects. So these useful kind of and generalizing effects are completely not seen by current interpretability schemes. And so in some sense, they're potentially treated as dark matter, for example. In autoencoders, there's a notion of dark matter, and so more or less these Gaussian fluctuation effects should be part of that dark matter. And so our team at PIBS is currently running collaboration with Synthesis to try to improve this state of affairs and design tools that are more compatible with these fluctuation effects and understanding the useful randomness. But there has additionally been a very significant amount of progress in the last couple of years that I think is a little bit invisible in the interpretability community, or hasn't yet percolated, that understands and interprets these effects, this kind of phenomenon, and in fact uses this to find very deep interpretations of realistic neural networks, or maybe of like interesting toy models, let's say, in a much more general context. So I think people in the AI safety community who I talk to mostly, who have heard of this at all, think that this is a certain kind of very, very small phenomenon that maybe is only present in something called the lazy learning regime. But in fact, there is this kind of very significant now body of physical literature that understands these random effects of the shape in a very general context. And this kind of very generally goes by the name of mean field theory. Again, there's a more narrow notion of mean field theory, but increasingly it's becoming a general purpose tool. And so this is a method, again, from physics. And physics, it gives approximate solutions to statistical systems. So statistical systems like magnets are notoriously hard to understand completely. And so physicists love getting and using approximations that are often very, very good. And in fact, in certain contexts, very exact, can become exact in highly connected contexts. So in particular, neural nets, if they're fully connected, are one of these. So by exact, I mean kind of increasingly good as we vary some parameter. So these approximations try to simplify the system, and in particular, mean field theory decouples a complex physical system into kind of two moving parts. And so the first part is macroscopic parameters. They're called order parameters, and they're things like pressure or temperature. And the key property of these parameters is that they do not macroscopically fluctuate. So if you look at for example, ideal gas in a box, and you look at any particle, well, it's gonna like move around a lot from like one side of the box to the other side of the box. You can't really have a very good guess at any point in time where it's going to be located. But and so as a result, in fact, things like total energy or kind of these macroscopic parameters do actually change for systems like gas in a box. But because there are so many particles, and by the law of large numbers or by the central limit theorem, if I have some very, very bulk effect of a bunch of particles, so something like pressure or energy, it localizes, so it essentially becomes deterministic to a point where I can measure the temperature in a room and the pressure in a room, and it's going to be a pretty constant parameter. But of course, so these large scale parameters are functions of microscopic parameters. In the gas example, these are going to be the gas particles. And so I'm going to call the macroscopic parameters big A. So again, there are things like pressure. There are things that don't actually fluctuate. So even though they are random variables, they're deterministic random variables. They're pretty stable. And then my microscopic parameters are going to be things that are completely crazy. Like we have essentially complete ignorance of where any given particle is in a box after some period of time. And so the assumption that mean field theory makes, or that makes mean field theory works, is that the microscopic parameters are conditionally independent, or at least approximately conditionally independent, at given macroscopic, so these order parameters. So if I know the pressure and temperature of an ideal gas in a box, I don't know where any specific particle is, but I know the probability distribution on the location of particles, and these probability distributions are independent of each other, assuming that I know the pressure and the temperature. So the only dependency in physics language the only coupling between the particles in physics language is through these macroscopic parameters. So pressure, temperature, which again I'm calling big A. Why does this simplify the system? Well, I can now reduce a very complex physical problem to fixed point equation. So namely, I can start by guessing something like temperature and pressure parameters A. And then because all the small particles, all the small microparameters are independent, each one just reacts to these macroscopic parameters, again, in a probabilistic way. So given A, I have a known probability distribution on every parameter. And I draw all the parameters from this distribution, all the microscopic parameters from this distribution. So we start with some setting of variables, pressure, temperature, etc., of macroscopic variables. We deduce a bunch of independent probability distributions on the microscopic variables. But now, if we have these probability distributions, then we can just sample them a bunch of times, or we can do this either numerically or theoretically. And now, for any given sample, we can now go back and compute the macroscopic parameters. So I can guess the pressure in a room. I can that gives me some probability distribution on particles, and now I can then take that probability distribution and plug it back in and compute a pressure. Maybe a better value here would be something like angular momentum, but yeah. So at the end of the day, we have this this kind of two-step process where I take a large macroscopic parameter, I get a probability distribution of microscopic parameters, and then I get back a new macroscopic parameter, which is technically, I guess it is a probability distribution, so I take the average, but of course, since it's deterministic, taking the average is the same as just taking the value. And if, in fact, my physics solution is a solution, it is a stable equilibrium solution of the physics context, where I haven't actually told you what kind of thermodynamics context we're in, but if a solution exists and it's kind of physical, then this set of macroscopic parameters is going to be a fixed point. So again, this procedure T is what happens when I take macroscopic parameters, I sample microscopic parameters associated with them, and then I recompute the macroscopic parameter as a function. And so the meaningful solution is exactly this solution to this fixed point equation. What's called the macroscopic parameters are what's called self-consistent. So this is a physics context, but it turns out it applies in a surprisingly general way to neural nets. And there are, in fact, several different mean field contexts for neural nets. At least two fully distinct ways of setting up mean field theory, but for most of them, the microscopic, so the small kind of single particle parameters, are neurons. So remember, a neuron is not the same as a weight. A neuron is a coordinate of some hidden activation space that applies a nonlinearity. So you can think of a neuron as a row of a weight matrix. So as associated with a row of a weight matrix, because what every nonlinearity does is it takes the previous activation of a neural net, takes the dot product with a row of a weight matrix, with a corresponding row of a weight matrix, and then it applies the ReLU or whatever nonlinearity you have. And so in the mean field theory context, we think of particles as these kind of rows of the weight matrix, which we call neuron locations. So we in this picture, neurons are not just directions in hidden activation space. We also think of each direction as kind of having a physical location corresponding to the associated weight matrix row. And remember, the weight matrix rows are the things that get learned. So this is the thing that fluctuates that we want to kind of statistically model. And so we just think of this as kind of being a gas particle. So each weight of each row of the weight matrix is like a little particle that sits somewhere in this space of weights, and it's associated, it's labeled by the corresponding neuron. So then what are the macroscopic or order parameters? Well, the order parameters have to somehow see the data, right? Like neural nets don't learn anything without data. So macroparameters will be some kind of bulk behaviors of the inputs and their activation functions once we've chosen the weights. Maybe like a special case is in case the number of training data points is very small. We can actually view every data point by itself and every activation by itself as a macroscopic parameter because of the central limit theorem, because it kind of is summed out of so many neurons, it is kind of effectively large compared to the neurons. So there's a regime where in fact just every activation is topic. In general, this is not a regime where it's very interesting to be, but it's a certain interesting limit. And so this limit where the number of neurons is so large that even the kind of each input can be viewed as macroscopic. So in some sense, the number of inputs is small. This is a rare regime. It's called the neural tangent kernel regime. It's kind of a very degenerate limit of neural networks that doesn't actually occur in real life. There are some analogs of this limit that kind of that occur early in training, or maybe in some sense in simple networks like MNIST. But of course, general networks are more sophisticated, so they don't work in this regime. And kind of something that again I think is surprising to people in interpretability who I talked to who have looked at this before is that mean field networks, mean field models. So the picture that I explained are much more general than this lazy regime, and in fact, in some sense, they are completely general. So any generalizing neural network phenomenon with some very kind of small and kind of caveats that don't cause problems in real life. Any neural network can in fact be modeled, and any generalization behavior can be modeled in a mean field regime. There's some very small kind of extension where you do need the width to be larger, but it's larger. You only need it to be larger by a log factor. So the mean field regime is in some sense completely general in kind of a very strong way. However, there's a trade-off if we want to apply mean field methods to completely arbitrary neural nets. The number of macroscopic parameters of these order parameters when you interact becomes very large, and in some sense, at some point, it just becomes the entire network. So at some point, the macroscopic parameters that we're tracking are just like literally every possible configuration of neurons. So of course, that's not a very interesting thing to do in the limit, but this kind of generates at least in some kind of intuitive way a spectrum of this kind of trade-off where I can complexify my mean field parameters, so these macroscopic variables associated to data. And as I do this, I get more and more expressive power and kind of more and more understanding of sophisticated neural networks. One direction to take this is to find good trade-offs, where we can take a reasonably simple model that actually completely describes an interesting behavior. And I think a kind of amazing result in an amazing paper is that this completely describes grokking. So here there's some small print that this is grokking in the mean square error context, which is not that different from Neil Nanda's grokking of modular addition. So this is a famous neural net where the process is understood, the idealized process is understood, but like there are some kind of mysterious things like this phase transition weird phenomena associated with like exactly how do neurons learn and exactly what signal do neurons learn, what noise do neurons learn that people have noticed. So for example, people like observed that every neuron is only associated with one modular addition circuit. So these are indexed by Fourier modes. And this was somewhat surprising because a priori you could have multiple ones. But this mean field theory solution actually completely predicts. So applying this, finding a correct trade-off in this context turns out to be possible in a kind of using a very elegant trick, essentially reducing to like a very small set of correct macroscopic parameters, and then we completely actually predict every single neuron's behavior statistically in a modular addition circuit. We understand why neurons only contribute to one circuit, and we have this kind of like incredible like maximal prediction of a model, which I think like doesn't exist more or less in any other context for a model of this complexity. So this again, this picture works in real life and it works for interesting contexts like modular addition. And so one of the authors of this Rubin paper is Zohar Ringel, and I'm actually working on a project with Zohar where we're kind of taking a similar idea with like a little extra wrinkle of complexity to explain context that includes superposition. So modular addition does not have sparsity or superposition, so SAE doesn't actually like give you information about it. But it turns out that in some superposition context, you can also apply mean field theory. And again, there's kind of a correct trade-off between the complexity of what you track and the expressive power that completely expresses certain like very, very interesting phenomena that we expect to happen for networks that take advantage of sparsity. So this is the general theory. I have probably about another half hour explaining a little bit more of like what exactly the interesting hyperparameters are. I think I'm going to mostly skip this and maybe send the notes on the Discord. Yeah, but maybe a key word that I'll say is that again there are different ways of thinking about mean field theory in a neural network context, and one way is what's called kernel methods. And so the interesting thing here is that the macroscopic parameters that you're tracking are not activations, but they are these dot products between activations, and so this is something called the kernel. Because of symmetries, actually these dot products in some sense completely determine the dynamics. They completely determine the velocity. And bulk properties of these, so something like let's see, bulk properties of these kernels. Sorry, this is the kernel. So I take the activation at the layer L for input alpha and the activation layer L for input beta. Take their dot product. I get an input number of inputs by number of inputs matrix done by a matrix. This is called the kernel. And so this kernel is often too big. There are too many parameters for them to be viewed as macroscopic. But you can do something like take the top eigenvalues of the kernel or restrict this kernel to have a particular shape, and then you're back in this mean field theory context where you have these macroscopic parameters. And you also the key observation is that like each of these entries of this kernel is a sum over neurons, because when you take two dot products, of course, what is a dot product? It's a sum of products of coordinates. So at every neuron, you take the two associated coordinates, you take the product, and you sum these together. And so you get exactly the kind of phenomenon you see in an ideal gas, where there is some quantity associated to every neuron. It's highly fluctuating, it's highly random, but then you sum all of them together into this kind of like more macroscopic thing, the kernel. So again, in general, this kernel is going to be too big to actually behave well, and so you want to reduce it somehow by maybe doing some things like you see. And yeah, so just taking this picture gives you some surprisingly nice. I mean, in some sense, this picture is fully general, though these kernels can become like arbitrarily complicated. The reason is in some sense that like up to symmetry, any collection of activations actually is completely determined by its kernel. So the kernel seems like some kind of big Gaussian sort of soft parameter, but actually it contains complete information about the state of your system. But thinking in this language is very useful, and it has as special cases many kind of other known approaches to neural nets. So for example, the neural tangent kernel is a special case of these kernel methods, and many results in this field called NNQFT. So there's this paper or book on principles of deep learning theory, which kind of extends the neural tangent kernel, and essentially more or less all of these methods can be understood as certain modifications of this kernel mean field theory. So hopefully I've like convinced you that this is an interesting thing to look at. So I think this is my final slide is that so neural tangent kernel is a special case, and then the other interesting thing to do is to kind of have some ansatz for what the kernel is. In particular, this Lee-Samplinsky ansatz is take the neural tangent kernel and just multiply by a scalar. And so these give you surprisingly powerful predictions. So in particular, Lee-Samplinsky is like a very powerful, kind of predicts some coarse grain scaling behavior of realistic networks in a surprisingly good way. It's of course not completely general, but in some sense it's scale general. And so upshot is that there's a number of methods in theoretical interpretability literature that kind of fall under this mean field umbrella. They're much more general than people used to think. In particular, they apply significantly beyond the neural tangent kernel context, and they explain things like rocking. They are compatible with sparsity, and it would be extremely useful, and I think in some sense imperative, to understand how these kinds of phenomena that again like are engaging seriously with randomness and engaging seriously with the fact that randomness can be used in a productive way in the computation, how these phenomena interface with existing interpretability tools like SEs. So that's the end of my talk. Let me see if there are any questions.
Yeah, thanks a lot, Dmitry. I think a really engaging talk, and yeah, thank you for making everything work with the slides as well. And if you can like also give us the link to the slide, those will be great, because we can use it later on and people can look through it. I think there's one question from Devon about like, my impression is that people have been applying MFT to neural networks for many years, but nothing super striking from a pragmatist perspective has emerged out of it. Do you agree? What's the idea or angle that past MFT work has missed that suggests that we'll get a ton of juice out of the technique now?
Yeah, so in some sense, most past MFT work is more or less in this Lee-Samplinsky regime. So it like makes some really strong assumptions on the kernel that essentially put you in something like the neurotangent kernel regime, the lazy learning regime, which again does not explain real networks. Yeah, and I think that the exciting, I think those papers are quite good. In general, they are theory papers, and somehow like it is a really, I think, big question to try to make them pragmatic, at least pragmatic to the extent that sparse autoencoders are pragmatic. So to get them to give us some extra juice in interpreting realistic models. But I think the new stuff is basically that we've gone past this kind of slightly restrictive regime, something like the Lee-Simplinsky regime, which restricted the class of neural networks that it applied to, and so now, for example, in this Noah Rubin paper on grokking, you're kind of like, it kicks you out of something called the Gaussian process paradigm. So in particular, neurons are no longer assumed. So remember, we have these macro parameters, and they impose some assumption on neurons. And in the past, basically all assumptions were that neurons are Gaussian, or approximately. So this distribution on neurons is a single and like pretty simple Gaussian, which is maybe like the NTK Gaussian, or like a rescaling of it. So this is again restrictive and did not describe real networks. But if you relax these assumptions, then you can describe every neural network, right? Because every neural network has some collection of neurons. You can just, turn any collection of points into a probability distribution in a stupid way. This is not really saying very much, but like, I think the new ideas that I'm excited about in neural field theory are essentially kind of like, again, as I said, splitting the difference between. So your this probability. So again, remember, macroscopic parameters are some like maybe bulk data properties, and then they lead to this probability distribution, which is assumed independent on neurons. And so the new thing is you relax this probability distribution of Gaussian. You say, well, this probability distribution can be maybe a mixture of Gaussians. So this is what the grokking paper does. The grokking paper says, well, probability distribution is going to be a mixture of there's an old Gaussian that's NTK that's like boring memorization Gaussian, and then there's a new Gaussian for every new circuit, for every Fourier mode, and these get mixed. And this completely explains the model. So in general, you want like some more general, more interesting probability distributions that are theoretically or empirically tractable, but that don't import these like old, very restrictive assumptions that essentially put you into this tangent kernel paradigm. So again, I don't think that this is like like something that people didn't expect, but I think increasingly it's being realized that this can be applied both in theory. Well, okay, currently in theory, it would be very cool to apply it in practice. I think it hasn't yet been applied in practice, but in theory, this can be applied in more and more general contexts, and there is, in some sense, no reason to restrict yourself to very simple models. So that's at least my sort of approximate answer. And I think that just generally kind of the field progresses, and so increasingly we see these non-neural tangent kernel, non-perturbative pictures that like get little pieces of complexity of real neural networks. So yeah, so I'm generally very optimistic about this, and I think that the thing that like really has not seen that I think is very, very neglected, and in some sense is one of the key reasons we're doing this collaboration with physicists, is then taking these new ideas and even like some of these old ideas and trying to convert them again into tools. So again, probably a lot of the dark matter in sparse autoencoders is just kernels, and so if we could understand this kind of like how kernels combine with sparse autoencoders, we'd probably just get a lot of mileage in better interpretation. So yeah, so this is kind of a whole picture that's completely neglected, that nobody has thought of seriously. And I would encourage you guys, if you have an idea, to try to come up with a model of how this can work.
Awesome. Thanks a lot, Dmitry. I think like if folks have any other questions, just feel free to add it on the comments. But yeah, thank you so much for putting this together, and also like staying way over time. Thank you for that. Yeah. Okay, I'm gonna stop the recording, but yeah, feel free to stick around, Dmitry, if you want, on the office hours as well. We have starting in almost 1.5 hours. Yeah.
Okay, great. Thanks.
Yeah. Thank you.
Bye.
Bye, everyone.